Okay, we've got a worked example here, which is a hypothesis testing question for the normal distribution. This is to do with a matter of physics, Ocron length, whatever that is. Quite an old question, as you can see. Anyway, so it starts off, a random variable x has the distribution normal with a mean of mu and variance of sigma squared. The mean of a sample of 5 observations of x is denoted by x bar. State the distribution of x bar, giving the values of any parameters. Okay, so now if we recall the sampling distribution video, which I'm assuming that you have seen, it refers there to the central limit theorem, which states that the distribution of sample means, the sampling distribution, approximates to a normal distribution as the sample size gets larger, regardless of the population's distribution. Okay, and then he goes on to say sample sizes equal to or greater than 30 are often considered sufficient for the CLT to hold. Well, that is sort of right and relevant if the underlying distribution is either not known or is something other than the normal distribution. We talked about uniform distribution in that video. If the underlying distribution is actually normal, then you don't have to worry about this limit of 30 because you basically will have it'll basically be the normal distribution anyway. So the distribution of sample means will be normal for values less than 30, and that's what we've got here. It's this underlying distribution for the random variable x. It is normal, and we've got a sample of only 5 observations, but it's okay because the sample mean, which we denote by x bar, will be normally distributed. Now, and also referring back to that video, we'll see that the variance of this distribution of the sample means is going to be equal to the variance of the underlying distribution divided by the sample size 5, and the mean, of course, is the same as we would expect. So that is it. Basically, that's the answer to part 1. It's normal with a mean of mu and a variance of sigma squared divided by 5. Now we're going to apply this in part 2. This is a good example of where forming your hypotheses is not necessarily straightforward. Let's have a look. A group of scientists is attempting to identify subatomic particles called Ocrons. Ocrons have a mean path length of less than 42 centimeters. The path lengths of a random sample of 5 particles thought to be Ocrons are measured, and the mean path length of the sample is found to be 36.6. Path lengths are known to be normally distributed random variables with a standard deviation of 8 centimeters. Carry out a test at the 10% significance level of whether the population of mean path lengths is less than 42. Stating your hypotheses clearly. Now, this seems a bit odd, doesn't it? Because we're actually told that the mean path length is less than 42. That is known. But really, the only thing we've got to go on is this 42 centimeters. So this has to come into our null hypothesis. But again, this is where it's a little bit confusing because this 42 centimeters is like an upper limit, isn't it, for the Ocron lengths. So that is what we're testing. The hypothesis is that the mean of the upper limit of Ocron length is 42. Right, it's not terribly straightforward, is it? But so we haven't really got anything else to go on but the 42. So our alternative hypothesis is that this mean is less than 42. test whether the population mean path length is less than 42. Okay, so so this is what we've got, is that the mean equals 42. The alternative is that the mean is less than 42. So one tail test at 10%. We have our test statistic here, 36.6, and if we just draw the bell shape here, and so this is our 10% down here. So so what we're looking at. So this is the distribution we're talking about. This 8 squared divided by 5. That's the standard deviation of the Ocron lengths. And that equates to this 3.578 squared. So the standard deviation 3.578. So we with this test statistic here, our mean and standard deviation can plop those into the calculator and find the probability that a sample mean is less than or equal to 36.6. And that's going to be a probability. So this is 36.6, assuming that the upper bound, the mean upper bound is 42 centimeters. And that gives us a probability of 0.066. So this, that's the 3 decimal places. So this is the P level, and it is less than the alpha level. So we would accept the null hypothesis that the mean length is, well, the mean upper bound for the length, should probably more correctly write, is 42 centimeters. Okay, so we're not saying that that is the mean. That's the mean upper bound. Yeah, not quite straightforward, is it? But you know, it is the sort of thing that might come up, and I think it illustrates quite nicely how some of these things can be phrased quite confusingly, and this is one such question. But hopefully that has been useful. So thank you for listening.